So, what if you could build one of the most powerful theoretical devices in the world, a quantum computer? But get this, using the regular old computer that's probably sitting on your desk right now. I mean, a machine like that could solve problems we can't even touch today, like designing brand new medicines or creating impossible materials. It absolutely sounds like something out of a sci-fi movie, but today we're going to explore this really wild idea of how it could actually be woven into reality.
You see, the whole challenge of simulating a quantum computer comes down to this fundamental mismatch. We're trying to get a machine that thinks in absolute black and white, zeros and ones, to dream in the infinite fuzzy shades of quantum reality. It's a heck of a puzzle.
And that really gets us to the big question, right? How can a machine that's built on certainty and clear, distinct steps ever hope to simulate a world that's all about probability, uncertainty, and everything being connected to everything else?
Okay, so here's where the problem really hits you. On the left, you've got your normal computer. It's discrete. Think of it like a digital photo. It's made of individual pixels. Sure, you can add more and more pixels to make it look smoother, but if you zoom in far enough, it's always just a collection of little separate points. But then, on the right, you have the quantum world. It's continuous. It's like a seamless, flowing reality with no pixels, no breaks. It just is. So how on earth do you bridge that gap?
Well, it turns out the solution isn't to try and change the computer itself. That would be impossible. Instead, the idea is to give the computer a new playground, a different kind of material to interact with. And this is where we introduce a sort of conceptual bridge to connect these two very different worlds.
And that bridge, we're going to call it a fabric. Just imagine a stretchy, continuous sheet. This fabric represents the seamless nature of the quantum world. Now, the classical computer won't become this fabric, but it's going to interact with it, learn from it, in a really profound way. So how does this actually work? Well, first you start with what the computer knows, its grid of discrete points. Then you use that grid to probe the fabric. You poke it, you measure its tension, you see how it stretches and bounces back. And through all this interaction, this network of points starts to learn. It starts to behave like the fabric, and it gets so good that it ends up creating this incredibly accurate simulation of that continuous reality, all inside its own discrete system.
But hold on. Just simulating a plain, empty sheet isn't going to get us a quantum computer. That's not enough. We need to introduce the actual building blocks of quantum information. We need to bring this fabric to life and give it those weird quantum properties.
So for our fabric to really be a true quantum simulator, it has to be able to represent the most fundamental thing in the quantum world, particles. So the question becomes, how do you create something that acts like a particle on our conceptual sheet of fabric?
And this is where we get to the qubit, the quantum bit. In this model, a qubit isn't just some abstract piece of data. It's something you can almost picture, a tiny, localized twist in the fabric. And this twist has a very specific, very weird quantum property called half-integer spin. Now, don't worry about the physics behind that. Just think of spin as a basic property of a particle, kind of like its electric charge. This specific type of spin is what makes the twist behave exactly like a real quantum particle, which makes it the perfect stand-in for a qubit.
And these twists are really special. They act just like quantum particles. But here's the crucial part. Every single twist is entangled with every other twist on the fabric. What that means is, if you affect one of them, you instantly affect all the others, because you're literally changing the shape and tension of the entire sheet. So when our computer probes these twists, they behave exactly like qubits are supposed to.
And that right there, that's entanglement in a nutshell. It's such a cool way to visualize it. Because all the twists exist on the same piece of fabric, they are fundamentally connected. You can't separate them. They aren't individual points anymore. They're just features of one single unified system. That's the secret sauce that makes this a quantum simulation.
Okay, let's just pause for a second and take stock. We've taken a normal computer, we've given it this conceptual fabric, we've put little twists in that fabric that act as entangled qubits, and now we have a working simulation of a quantum system. The design is done, the machine is built, so what do we do with it? And just like that, we've done it. We've arrived. This fabric with its whole network of interconnected, entangled twists, that is the quantum computer we set out to build. We have, for all intents and purposes, created a quantum brain inside a classical machine.
And that leads us to this really powerful final thought from the source material. We've built the tool. The next challenge, and maybe it's an even bigger one, is figuring out what questions to ask.
How do we even talk to this complex, interconnected system to get answers that mean something to us?
So, I'll leave you with this thought. This whole model gives us a completely new way to think about building a quantum computer. The final hurdle isn't just about the engineering anymore, it's about imagination. If you had this incredible machine at your fingertips, this simulated quantum reality, what cosmic secrets would you ask it to unlock?